Facades being vertical surfaces are far more challenging to harvest water on in comparison to horizontal surfaces. Figuring out a way to harvest water on a vertical surface became the first major design challenge. After several attempts at methods to try to harvest water off a vertical surface, the aim was to create surfaces with different topographical qualities. And using computer simulations and generative design tools such as Grasshopper to then predict possible water flows on these surfaces, and then use that to create patterns on the surface that would control the water flow and direct the water to catchment areas. Over the next few pages, you'll see many iterations from Grasshopper that attempt to approximate water flow using gradient descent definitions. After studying 3 different surfaces, a single surface was shown for further observations. Here on these 2 pages, you see many diagrams straight from out of Grasshopper. These diagrams attempt to describe and approximate the flow of water on this particular surface given an even distribution of water. There were also further diagrams done describing the possibilities of the intensities of the patterns on the surface in order to gain an appropriate level of control on the water flow. Based on the results from these iterations and computer simulations, the single surface was modified and refined further to better control the water flow. Here we see a series of physical simulations performed on physical clay models. Here we observe the first of the many phenomena. We have a smooth clay surface with a hole in the center. That hole is the stormwater catchment area, and the aim is to direct the water flow to that point. The first of which was a circular technique, which allowed the water to smoothly flow past the catchment area, while the second technique was a zigzag technique, which involved using back and forth motions from the catchment area to the outer radius, and that proved to be more effective in controlling the water flow and directing it to the catchment area. At this stage, the surface is to be populated with carvings from Grasshopper iterations which predicted the water flow. These carvings or marking on the surface can be described as channels, as they aim to direct the water flow from one area to another. 2 shapes were considered for the profile of these markings, a square profile and a triangle profile. The square profile showed to be less effective, as it carved more deeper corners into the surface. This allowed more opportunities for the water to be stored there. The square profile didn't seem to be very effective. It carved more corners into the surface, which provided more opportunities for bodies of water to form. This would in turn house more bacteria, and the bodies of water could interfere with the water flow. Another shape that was considered was a triangle. The triangle seemed to be more effective. The triangle profile was more effective, as it usually only seemed to carve out one corner out of the surface. This encouraged better water flow and eliminated the opportunities for bodies of water to form. It also provided some other logical benefits. Triangle forms are harder to climb and easier to access and clean. These triangular profile channels were carved out of the clay for further physical simulations. Once the channels were carved out of the clay, it made a huge difference to the control over the water flow. With a smooth clay surface, it was almost impossible to control the water flow, and now with these channels, it is very efficient and effective to control the water flow and direct it to these water catchment areas. The effectiveness of these channels is clearly highlighted in the attached videos of the simulations. These channels proved to be very effective in both situations, although they seem to be slightly more effective in shallower sloped surfaces, such as the second simulation. All these patterns which dictated the direction and the length and the magnitude of the channels were generated in Grasshopper, as it can be seen with this script here. This is a recursive Grasshopper definition. All these patterns and all these channels were developed in Grasshopper using this definition, as it can be seen here. This is a recursive definition, which means the results of one event become the input of the next event, and so on. A number of parameters can be controlled, such as the detail of the simulation of the water flow, both in the U and V numbers, as well as the factor which controls the strength of the gradient, which determines how fast the water travels along that surface. In addition to the channels on the surface of the facade itself also houses some water storage systems. There are at least 2 water storage systems for every level which supply water to the surfaces of that level. These water storage systems can be seen as localized low-volume water tanks on every level. And of course the water in these water storage systems would be treated to kill any bacteria. The structure of these low-volume water storage systems consists of metal edge beams with truss members in tension, since the whole water tank is in tension. A fully parametric 3-dimensional structure of the water tank was developed, and the Grasshopper definition can be seen here. Storing water on a facade has certain advantages. Firstly, water is a great thermal insulator. Secondly, it saves the water being taken down to basement only to get pumped back up to the levels. Thirdly, the water is constantly exposed to thermal radiation, which means it benefits from qualities of solar hot water. Furthermore, the facade has its own irrigation system embedded inside the facade, and this consists of mainly 2 sets of pipes. The blue set of pipes represents the stormwater, and the red set of pipes represents the overflow. The stormwater is collected from the roof and from the water collection points on the facade and is then equally distributed to the water tanks. The pipes are arranged such that all the water tanks fill up simultaneously. And once the water storage system fills up, the overflow leads to the water tank below. That assures that the water on the facade is used as efficiently as possible. Once all the water tanks are full, any excess water on the facade simply falls down and turns into a water feature near the ground floor, near the entrance. Any additional water goes down to the basement, which gets circulated back into the system. Here we can see a section through the water storage systems and the pipes. We can also see the water catchment areas. The water catchment points are designed such that in case if there's any water which escapes that water catchment point, it is directed to the next water catchment point, which is below. This facade system, consisting of the water catchment areas, the channels and the carvings on the facade, as well as the water storage systems, ensures that any water that falls on this facade is used to its maximum efficiency. And once all the water storage systems are full and the water can no longer be stored anywhere, the water just continues to flow down the facade and turns into a waterfall near the entrance, which then goes down to the basement and is recirculated through the whole system. This has been my facade water system for the Waterworks cluster. Thank you again for listening.